which you're invisible mass acting on dark matter. And I know it sounds kind of just like a flashy title, but I do want to emphasize that these things are kind of close to invisible. So this is a plot that I really like from the snow mass report, which is the interaction strength of your dark matter candidate versus the dark matter mass. So you can think about it as you go down in interaction strength, your interactions are less and less likely to happen. So you have a rarer process. And as you go left on this plot, each individual dark matter particle has less energy to deposit in your detector. And so we're talking about looking down in this bottom left corner of this plot in the low mass axion area. And so these really are like kind of invisible, but we do think that we can go out and look for them. And so that's what I'm going to tell you about today. Okay, I have to click here. Okay, so why do I care about axions? Well, I'm not alone. This is a plot of abstracts submitted to the APS April meeting with the keyword axion or the keyword wind. And you can see in red are those axion abstracts, and you can see we have this nice exponential rise in interest. Clearly, people are really excited about this. And this is for a couple of major reasons. One, we finally have the technology to go looking for these sort of invisible particles. We have advances in cryogenics, magnet technology, and quantum sensing that are enabling these searches. And the other side is that there's been a lot of theory advances recently, which are motivating looking for axions over a much wider range of masses, and suggesting all sorts of interesting cosmological histories and things like this. So it's not just that they're sort of popular, but they're also very well motivated particles. And so I'm going to walk you through some of this motivation right now. So axions are not originally hypothesized as dark matter candidates. They're hypothesized as a solution to something else, which is the strong CP problem. It's this problem with quantum codewine dynamics. And in a nutshell, this problem is that the strong force should violate CP symmetry, but it appears not to, at least to a very, very high degree of precision. So you might say maybe just the standard model thinks of CP symmetry as a good symmetry. Maybe this is just something that nature has decided for us. But we know that in the weak sector, this is violated. So that can't be the case. So we should have some reason why we have the CP symmetry. And so if you write this out in mathematical terms, if you go to the QCP in, you have this term right here. And this is the term which explicitly violates CP symmetry. So the amount of CP violation in the strong sector then is determined by this coefficient theta bar. And if I write out theta bar, you can see that it has two different terms. The first one, theta, comes from the fact that QC has multiple vacua. And the second term right here, this is the quark mass matrix. This just comes from the fact that quarks have mass. So these are two different angles, but they're from totally separate areas of physics. So when you add together two random angles, you should expect some arbitrary angle between 0 and 2 pi. And so you would naively expect this to be an order 1 number. But remember, I told you that we have found that there is basically CP symmetry in the strong force. So for some reason, theta bar is 0 and not order 1. How do we know this? Well, we can actually basically directly measure theta bar. And we do that with measurements of the neutron electric dipole moment. So you can see this right here. This is the neutron EBM, and it's proportional to theta bar. And this plot, all these red points, are upper limits on the neutron electric dipole moment. And you can see over the past many decades, these upper limits have gone down by many orders of magnitude. And we're now at this sort of ridiculously small number of 10 to the minus 26 electron centimeters. So if you do a quick division, you can see that we have experimentally found that theta bar has to be less than 10 to the minus 10. So this is really, really tiny. This is a huge fine-tuning problem because somehow we have these two random numbers canceling each other out to better within 1 part in 10 to the 10. That should make us very uncomfortable. So back in the 70s, two theorists came up with a solution to this problem. They said that there had to be some symmetry, which was broken in the early universe at some very large energy scale that we can write as x of A. And when that symmetry is broken, you end up with this axion field A. And the reason why this is relevant is when you have this new field, you get a new term in your Lagrangian with the exact same form. So we now have this sort of combined coefficient right here. And you might be saying to yourself, wait, this is more of a problem than a solution, right? We now have 3 things that have to cancel each other out instead of just 2. But this is actually much, much better because theta bar is just a static number, whereas A is a field, it's dynamic. And so we can see how it actually evolves in its potential. And of course, if you write down the axion potential, you can see that there is a minimum right at theta bar. And so going back to that first physics class we ever took, it doesn't matter where the ball is on the hill, it's going to roll down to the bottom. Okay, and so now we have A over F sub A equals theta bar, and this naturally goes to 0, and we can naturally have CP symmetry in the strong force. So check, we've solved the strong CP problem. But going back to this picture over here, we know the ball isn't just going to roll down to the bottom and stop there, right? It's going to oscillate around the bottom. And of course, this is a new particle associated with the field. This is the axion particle. This oscillation oscillates with a frequency that is m sub A, that axion mass. So we solved strong CP, and now we've created a new particle. And anytime we create a new particle, we should ask ourselves, does this particle have the right properties to be the dark matter? And of course, you already know the answer to this question. Axions are a great dark matter candidate. They are a particle. They have a mass that's in the correct mass range, although that's not a very stringent requirement, I'll admit. It also automatically comes with very feeble interactions with the standard model particles. And it has feeble or non-existent self-interactions. And the way you create it in the early universe, it's very easy to create it with the right energy density to be all of the dark matter that we have today. And then finally, that production mechanism also produces cold axions, so we don't have to worry about particles zipping around relativistically, messing up our structure formation. Okay, so we solved strong CP, we have this great dark matter candidate. This is clearly something that we want to go about looking for. So how do we actually detect axions? So we have several different interactions we could choose from, but unfortunately, all of these are very feeble. All of these vertices have a coupling strength that is inversely proportional to F sub A. And remember, that's that very large energy scale. So these are very small couplings. Now, the experiments I'm going to tell you about today, and most axion experiments, look for the coupling to photons. And this is basically because we're very good at looking for photons. There are some experiments which look for some of these other couplings, but I'm not going to talk to you about that today. So in that sort of space of looking for photons from axions, this is the sort of canonical plot. We have here on the y-axis, this is the coupling constant, J gamma gamma, between axions and photons. And on the x-axis, we have the mass of the axion. I will point out that there are many orders of magnitude to cover right here. This is very unconstrained. And also, the units on this x-axis are electron volts. So if you look right in the middle, we're talking about something around a micro eV. So these are very, very tiny particles. This golden band here is what we call the QCD axion band. This is axions that have the correct combination of mass and coupling constant in order to solve the strong CP problem. So everything outside of this, we call an axion-like particle or just generically an axion. But these are really the most motivated axions that we're trying to go out looking for. Everything else can still be dark matter. It just doesn't solve strong CP. Okay, so now before I tell you a little bit more about the actual experiments that we use to look for this, I do want to take a step back and say that because these particles are so light, we can't look at these experiments as just a sort of a normal particle physics scattering experiment. If you think about a standard particle detector, you have some chunk of detector material, you have a particle come in and it scatters, and you can tell that something happened because there's some maybe energy deposition. The macroscopic view of this would be a pool table, right? You have a cue ball come in, it hit the balls on the table and they recoil, and maybe one falls in the pocket and you see that something happened. But because axions are so light, this just doesn't work. It's like taking a molecule of air and bouncing it off of one of those pool balls. Nothing is going to happen that you can actually observe. But fortunately, we're not stuck. Because axions are so light, if they are the dark matter, there have to be a lot of them. And so instead of designing an experiment like a pool table, we can instead design it more like a windmill. We're looking for the coherent effect of many axions, many air molecules interacting at the same time. And that's how we're actually going to observe these particles. We think of them more like waves than particles. Okay, so in that spirit of thinking about them as waves, instead of thinking about their mass, instead we can think about their wavelength. And this really defines the different detection regimes that we can have. So in the middle, I think is probably what most folks are familiar with when they think of axion detectors. These are cavity experiments like AEMX. And the sort of funny thing about this central regime at around a microelectron volt is that the wavelength of the axion is about the size of a person. And so what this means is that it's pretty easy to build experiments of that scale. And so when you think of a cavity experiment, you would just have the nodes of your wave that they can match up to the walls of your cavity. And so basically what happens is when the axion field interacts with your cavity, you can have it resonantly depositing energy there, bringing up your cavity. And that's how you do detection. Now, if you go to higher masses, the wavelength gets shorter. And so it gets hard to build experiments that are still sensitive with these, if you were going to try to take advantage of boundary conditions. So I'm not going to tell you about this, but this is the other sort of region that I work on. I work on the experiment BREAD. It uses a reflector, which looks for photons from axion conversion in a similar way to how telescopes work. So I'm happy to talk about this offline, but I won't talk about this anymore. Okay, so for the rest of the talk, we're going to be discussing low mass axions. This is when your wave is much, much bigger than a reasonable size experiment. It's hard to get funding to build cavities that are hundreds of kilometers in size. So instead, we have a different technique. And this relies on the fact that your wave is in phase across your entire experiment. And so this is the regime of lumped element circuits. So if you think about when you write down a circuit diagram of inductors and capacitors, you're sort of inherently making the assumption that everything is in phase across that detector. You can think about it in terms of voltages and currents instead of E fields and B fields. And this is what we're going to be doing for the DM radio experiments. I will note before I get more into the experimental stuff that these low mass axions are very well motivated. Here's just a handful of papers of people saying that this is the place you should look. If you have your high energy physics happening at the gut scale, you end up with axions in this low mass range. Okay, so moving on to experiments. So I worked on abracadabra for my thesis project. It was the first lumped element experiment to just show that this method works at these low masses. And now we're building a few different generations of the DM radio experiments, which are more sensitive. So DM radio 50 meter is the one that we're building right now. DM radio meter cubed is going through the Dark Matter New Initiatives program with the DOE, and hopefully we'll start construction in the next couple of years. And then finally, we have DM radio GAT, which is still conceptual, but it's this sort of large scale experiment. And I'll come back in the very end of the talk to discuss that. So how do these things actually work? Well, we're talking about waves, and we're also talking about electromagnetism. We're talking about photon interactions. So the correct set of equations to describe this is just basic Maxwell equations. So here in white, I've just written classical Ampere's law with no sources. So we have the curl of B is dEdt, or the displacement current. Now, if you have axions, they will cause this modification that I've drawn in orange. And you can see that the magnitude of this effect is controlled by this very small coupling constant J gamma gamma. So this is a very small change to Maxwell's equations. We have two terms right here. And the first thing I'm going to do is I'm actually just going to get rid of that first term because we expect the gradient of the axion field to be small. And so what we're left with is this term right here. And you'll notice that it looks a lot like this displacement current term. So what I'm going to do is I'm actually just going to rewrite this new term as an effective current that can be a source for a magnetic field. So here we have the known form of A. I can plug that in, and this is what I get. I have an effective current that's equal to the coupling constant times the square root of 2 rho dm. Rho dm here is the energy density of dark matter axions that are going through my detector at any time. So if I have a higher energy density of axions, I have a larger signal. This current oscillates with a frequency that is the axion mass, and we don't know what the axion mass is. And it's proportional to B. So this is a magnetic field that I supply in my experiment for the axions to interact with. And when they interact, they create this oscillating effective current that is parallel to those magnetic field lines. And so that's the signal source that is I'm looking for in my experiment. So that's the signal. And here's the detector. So I told you we can just write it as a lumped element circuit. You can see we have a bunch of inductors. These are all lumped elements that are sort of components of the experiment. And I'm going to step through this sort of schematic diagram before I tell you what the detector actually looks like. So the first thing we need is we need a magnetic field to source that effective current. And so I can, in my circuit diagram, just write this as an effective current source. But now we have an effective current, and I want to turn that into a real current that I could detect. And so I have an inductive coupling. It's basically a transformer between the effective current and my wiring. Once we have that transformer coupling, we end up with a real current circulating in wires. But of course, it's a very small current because it's proportional to G gamma gamma. And so I need some sort of very sensitive current sensor in order to detect it. So I've written it here as a squid, although it doesn't have to be a squid. And then finally, once my current sensor has amplified that signal, I can read it out and digitize it and analyze it offline. So this circuit that I showed you is a broadband circuit. It didn't matter what the frequency was of this signal. All of those signals could equally well get through to be read out at the end. But I can actually play a trick. If I add a capacitor right here, I can turn this central element into an LC resonator. And the thing that's nice about this is if the axion frequency matches the resonance frequency of this resonator, then I can resonantly ring up that resonator. Lots of resonances there. And And the nice thing is that we expect quality factors of resonators of something like 10 to the 6. And that determines how much enhancement you get. So if I have a 10 to the 6 quality factor resonator, I can have 1,000,000 times enhancement in my signal strength. And that's really great. But of course, there's a catch, which is that I don't know what my axion mass is. And so I have to tune this capacitance to tune that LC resonance in order to look over the space of different axion masses. Now, this takes a really long time, but it turns out that this enhancement is worth it. And so this will help us win in the end. So the prototype experiment, Abracadabra, just used a broadband approach to show that this technique worked, but all of the DM radio experiments will use a resonator. Okay, so what does our signal actually look like? So first, we just collect our data as a time series, and then we Fourier transform it to look in frequency space. If we were to have a broadband experiment, our background looks like this. It's just flat with respect to frequency. If we have a resonator, we'll have some resonant line shape. On top of that background, if there's an axion signal, there'll be a very sharp peak with a frequency that corresponds to the axion mass. If you zoom into that peak, it is very narrow, but there is some width, and that width is determined by the velocity distribution of the dark matter axions. That's kind of like a Doppler shifting. So this line width is something like 10 to the minus 6. Its shape is determined by what halo model we use. Most experiments, including the ones I'm working with, for a baseline, just use the standard halo model, but we definitely have room to put other sort of exciting things like streams and other things in there. Okay, so our sensitivity then is determined by how fast we can scan over masses while maintaining a certain sensitivity. And so this is the scan rate. The first part just contains all the axion physics, that's stuff we can't change. And the second part contains all the detector physics. Okay, so just to lay it out, this first term is a coupling constant. This is saying how well coupled is our pickup circuit to the axion effective current. Up here on the top, we have the quality factor of your resonator, the magnetic field strength and volume. So if we have a larger, stronger magnet, we have a better signal. And on the bottom is all of our noise. We have thermal noise and amplifier noise. And I'm not going to talk a lot about some of these other terms, but I do want to talk right now about the geometry and how that affects the experiment. So the first choice you have when you're actually building an experiment like this is if you want a toroidal magnet or a solenoidal magnet. The toroidal magnet has some advantages. Basically, you have a field-free region where you're looking for your signal, and you'll see how that works later. But as you go to higher masses, like DM radio meter cubed will, it turns out that you run into parasitic resonances. And then I'll come back to that when I talk about DM radio meter cubed. So I'm going to frame all of this for the 50-liter experiment. But these two geometries are very similar. Basically, if you cut the toroid and unwind it, you'll get the same thing for the meter cube experiment. So if you like thinking in solenoids, you can cut all of my diagrams and unroll them in your mind. Okay, so let's look at the 50-liter detector. So I put the circuit diagram down here just for reference. Again, the first thing you need is a magnetic field. So for 50-liter, we have this toroidal magnet. It has magnetic field lines that go around like this. In the presence of axions, you end up with an effective current parallel to it, like that. And then because of that modification to Ampere's law, this effective current turns into a real magnetic field that by the right-hand law just wraps around. And so what we want to do is we want to sort of catch this magnetic field. And in 50-liter, what we do is we actually wrap the entire magnet in a superconducting sheath. So in order to sort of cancel out that magnetic field, you end up with currents that circulate on the inside of the sheath. And of course, it's not very good if they're all stuck on the inside. So what we do is we cut this sheath, there's a slit on the side, and those currents can come around and wrap around the top. And so now we have real currents running around the outside. I lied to you a little bit before. We actually have one more transformer step for sort of technical reasons. So these real currents generate a magnetic field, which in turn we can couple onto another inductor, which we place in this central region. And so now we have real currents running on this inductor. And in order to make this a resonator, we got a capacitor. Okay, so now we have currents that are being rung up on this LC resonator. And then we want to amplify them and read them out, which we do with a squid, not this kind of squid, a superconducting quantum interference device. Okay, so that's the 50-liter detector. Now we're still building it, but I did want to show you some data. So I'm going to show you some data from Abracadabra, but it will look very similar for 50-liter. And so you will sort of see how this process works. So this is the average spectrum from the most recent run of the Abracadabra 10 centimeter. We have power on the y-axis versus frequency. And just to orient your eye, nanometer the axion was just got there. Okay, so what do we do to our data to actually use it to look for axions? Well, the first thing you probably noticed is that there are lots of spikes on this data. And unfortunately, these are not all axions. There are a lot of backgrounds in this range, and we have to get rid of them before we can look for a spike. So some of these backgrounds that we found in ABRA will be the same as those in 50 liter, although I'm sure when we turn on, we'll find some new backgrounds to figure out where they're coming from. But I did want to talk about a few that we do expect will probably also be in the DM radio experiment. So the first handle that we have that's actually quite easy to get rid of backgrounds with is we can actually turn our magnet off. So we know that J effective is proportional to B, right? So if we turn B to 0 and the spike is still there, it's not a J effective. So you can see here in the blue is the magnet on data, and in orange is this sort of veto magnet off data. And you can see there are a lot of spikes where they're in the same place. And so none of those are axions, and we can get rid of them. Another one that we actually weren't expecting to see in the abracadabra data, but which we found, is we saw some spikes that wandered around in frequency space. So here we now have frequency on the y-axis versus time over the length of the run on the x-axis. And you can see this peak is wandering around in frequency space, and it actually persisted when the magnet was off as well. But because it was moving around, our initial veto for the magnet off spikes didn't catch this. But this is clearly not an axion. We don't expect the axion mass to be changing in time in this way. So that's also not an axion. And the other one that I think is kind of fun is that we're actually in the AM radio band. So we see AM radio stations in our data. It was a really fun undergrad project that we had her write a script to demodulate our data. We were able to listen to the radio through abracadabra. It wasn't very high fidelity, but we could listen to the music, which was kind of cool. This is a Spanish Christian station in Boston. You can see it looks like they might have a bit of an issue with their antenna. It's kind of wandering around a little bit, but this is at a known frequency, and so we can veto it. Okay, so once we have removed all of these spikes that we know are not axions, the next thing we need to do is we need to calibrate our data. We need to take these units of power and turn them into units of J gamma gamma. And the way we do that is with a full end-to-end calibration. So in abracadabra, we took a wire and we put it directly into the magnetic field and injected sinusoidal currents on that. And that is a very good mimic of the axion signal. You can see here we injected lots of spikes over our whole frequency range and at different power settings as well. And we were able to sort of deduce what our very linear response was in our detector. We can't just do this. We do have to do some numerical simulations as well of the entire setup to make sure that we really understand what's happening. And so we did those with console. And we were doing similar things for DM radio. So these left two are simulations of the axion signal itself. You can see here the red marks this sort of concentration of magnetic field lines in the center. And in the middle right here, you can see those flux lines are getting injected because there's a cylinder now placed in the middle that is canceling the magnetic field. Something we weren't expecting, again, for abracadabra, is that there was a bunch of parasitic in the wiring, parasitic inductance in the wiring. And so we actually simulated the wiring itself to try and get an estimate of how much parasitic inductance there was, and we plan to do similar things for DM radio. But we did learn we want to cut down wiring as much as possible in the updated experiments. Okay, so we've removed backgrounds, we've calibrated our data, and now it's time to actually fit an axion signal. And so what we do is we take the template for the standard halo model and we scan it over the entire frequency range to see if any remaining bumps match that template. And you can see here sort of a toy version of that. This blue is toy data. In green is what a signal would look like if it were at our 5 sigma threshold, so very obvious. And in orange, we have something that's right at our 90% confidence limit. Okay, so of course we didn't find any axions yet, but we were able to set world-leading limits on axion dark matter. The unfortunate thing is that abracadabra is up here, and the most motivated parameter space is all the way down here, right? So we have several orders of magnitude to go before we can reach those strong CP problem motivated axions. So the answer is, of course, DM radio, which is this series of larger experiments, and those will reach all the way down to the bottom of this QCD band. So now I'm going to dive into the DM radio program in a little bit more detail. So just to give you a little bit of a timeline, the first ideas for how to do these sort of lumped element experiments came out in sort of mid-teens. Abracadabra did construction and upgrades and results during my grad. This is basically my grad school right here. And in parallel, there was another group at Stanford that was working on a DM radio pathfinder experiment, which was a very similar concept, but using a resonator to look for dark photons rather than this broadband approach looking for axions that abracadabra did. But ultimately, we decided that it was better to work together than to compete. And so we joined forces, and we now are working together on this DRAM radio 50-liter experiment. And so right now, we are here, reaching the end of our sort of construction phase. Okay, so here we have DRAM radio 50-liter. This is the picture you've seen before. The 50-liter experiment is going to be a search for axion-like particles over a very wide mass range. This is some 3 decades in mass. And the goal of this 50-liter experiment is not only to put limits on axions, but also to be a demonstration of the scale-up of this technique. So we need to show that this sort of larger paramechanical design works. We need to show that this tunable LC resonator also works. And then finally, we also want it to be a test bed for the quantum sensors that will be critical to reach the sensitivities that we need for DRAM radio gut. So we're going to start out just using sort of a simple squid system, and then we'll upgrade to some quantum sensors that we're working on right now. Okay, so I'm going to show you some highlights from the progress that we've made on 50-liter. And I do want to note that all of these diagrams are preliminary. I didn't want to stamp preliminary on every single plot. Okay, so first, we've done a lot of electromagnetic simulations, which, like I said before, was very important for abracadabra and is even more important for 50-liter. This on the left is some simulations that I did. We have the inner and outer radius of magnet. And the color here marks how much energy we have coupled from the axion field into our pickup circuit. And so basically what this diagram is telling you is build your magnet with these dimensions, not those dimensions. So that stage is over. We've figured out what design we want for our magnet, and we're constructing it right now. These were some other simulations that were done by a grad student at Berkeley, Alex Droster, trying to figure out how much loss we would have in our system. So remember I told you we basically have to cut a slit in our sheath in order to get the signal out? Well, it turns out that whenever you have signal getting out, you can also have loss getting in. And so depending on how you design your magnet and your sheath, it will change how much loss there is. So critically, we have 2 separate halves for our magnet. Basically, you have them touching, you have another current path for the axion current to go around, and you won't have any signal. So here we have the amount of loss you have versus frequency for a few different configurations. So here we have if those halves are touching, again, this is not a good situation, you won't have a signal. And then if you change the gap between those magnet halves, you can see we have less and less and less loss. And so we are now firmly within the regime where this loss from the 2 halves of our magnet is not going to be driving the total loss of our system. Okay, we've also made a lot of progress on cryogenics. So we have this sort of funky dual cryogenic system. We have a sideways dilution refrigerator that mates with a larger 4 Kelvin system. So here's that sideways still fridge, here's that larger 4 Kelvin system. It's actually going to be on rails and it's going to slide in because we wanted a larger space and a larger cooling power to cool the magnet, but it's really important that the resonator package is at as low a temperature as possible. So you can see here's a little bit more on the cryogenics. A grad student at Berkeley, Aya Keller, has been working on the cold fingers that sort of slide into that 4 Kelvin system. We call it a cold snout. And then here are some simulations also run by Alex Droster, trying to figure out how fast we can cool down our magnet. And getting onto the magnet, this is probably where we've been doing the most work recently, is trying to make sure that this magnet is built properly. So here is a CAD model of what the magnet will look like. And here you can see some photos from the company SSI, Superconducting Systems Inc. This is the company that's winding our magnet for us. They're the same folks who did our magnet for abracadabra. So this picture right here is of the aluminum wedges that form the mandrel on which the wires are wound. It's about this big. And here is the winding happening itself. And this is actually slightly outdated. We now have 3/4 of our magnet wound already. More on the magnet. So you see on the left, we have to support the magnet somehow. Unfortunately, we're an earthquake country, which means that we really wanted to make sure that if there was any sort of shaking, we wouldn't have our magnet tip over and cause a huge quench. So we have really thought about this a lot. We have actually something like a shear wall that used for construction. We have that in our structures here. You can also see we have this insulating section because, again, we can't have any complete current paths that would screen out our axion signal. We also have this clever design that was done by grad student Jessica Fry at MIT for how we're going to strap our magnet together without electrically connecting them. We have these Kevlar straps that are held together by an aluminum spring. And this is something she designed with some engineers at Base Laboratory. And you can see this is various stages of testing to make sure that would have the critical requirements to hold together those two sort of heavy magnet halves. And it works great, and we're planning to implement this. Okay, the sheath. The part that goes between your magnet and the rest of your circuit. Very important that it has no loss for the axions, but also that it's lossy enough for when you charge it. So basically, as you charge your magnet, you're going to be inducing currents on your sheath. And the currents that are going to be induced from charging are going to go around like this, sort of coiled up to the center and then around. And if you don't have any loss right there, all of your currents are going to be on your sheath. And so we have this normally conductive gasket that's going like this in order to dissipate those currents. But because the axion currents go around like this, it shouldn't create any loss for our axion signal. And so Nicholas Rapidas at grad student at Stanford has been doing some testing of those materials and making sure that we have the right connections between our niobium sheath and this normally conducting gasket. The resonator. So also this has been a sort of multi-institution effort. The primary work on the inductor has been happening at Princeton, and you can see it's a little bit hard to see in this slide because it's very fine wires, but they're wrapped around this structure currently it's alumina rods, so we'll be shifting to sapphire, which has lower loss. You can see they put together an entire resonator in this fridge at Princeton, and they've been able to achieve quality factors of in the 10 to the 5s, which is already good enough for us to run, although we'd love to push that up to 10 to the 6. That would be really fantastic. And we've also been doing testing of different capacitor setups at Stanford in the dilution fridge itself. We've also been making a lot of progress on software. So Kelly Papas, a grad student at MIT, has been doing a lot of the work on the database and online monitoring system. We now have a bunch of computers set up in our lab at Stanford, and we're about to start doing testing actually in situ. I lead the calibration team, which is near to my heart because it was a really hard thing that we did on abracadabra 10 centimeter. And so this is just a couple of pictures from that. So for a 50 liter, we are again going to have a wire that goes through our magnetic field. But because we're a resonant experiment, if we leave that wire in, we will destroy our quality factor. And so we're going to have to take that wire out while we're running. So in addition to doing those sort of end-to-end calibration tests at the beginning of the run, we're also going to be doing calibrations downstream of our amplifier chain. And so this is one of those things we can do. We can actually, while we're running, inject signals in the side bands of our resonance. They won't interfere with our sensitivity to axions on resonance, but it will allow us to see what the performance is of this whole chain. And then in addition to this, we're also going to be doing other tests where we inject signals sort of in between data taking steps, again, farther down our amplifier chain. We have a dip probe set up where we're doing these calibration tests while the Delphi is being used. Okay, so that was kind of a whirlwind run through what we've been doing for 50 liter. Basically, I wanted to tell you that we have a lot of efforts going on right now, and we're hard at work getting ready to take first data next year. So the next thing I want to tell you about is the meter cubed experiment. So meter cubed, again, we're right here. We're sort of in the design phase. We're hoping to be reviewed by the DOE next summer, and then hopefully starting construction in 2025. So DM radio meter cubed has very different goals from the 50 liter experiment. Instead of being this sort of setup for R&D and then testing different things, we really are a QCD axion experiment. We're hoping to get down to the bottom of this QCD band at these higher axion masses. As you can see here, the plan is to hit DFSC from 30 to 200 megahertz, which is sort of in this intermediate regime between where we have a fully lumped element limit with a very long wavelength, budding up to where it starts to become more and more like a cavity. And this will become important, as I'll tell you in just a moment. So again, we're shifting to a solenoidal design. And this is because the toroidal design inherently has some capacitances which bring the resonance frequencies down. So we have 1 over square root LC is our resonance frequency, right? If you have higher capacitance, you end up with a lower resonance frequency. And this is a problem because we want to avoid parasitic resonances because we want to be able to tune what our resonance is, and we can't tune above that parasitic resonance. So what does this solenoid actually look like? So here's the sort of standard picture, right? We have the magnetic field going up and down, as is the axion effective current, which creates a real magnetic field here. And so you would naively think you could just pick up that magnetic flux with a loop right here. And you can totally do that, but we're actually going to do something slightly different. You can think of it sort of like duplicating. So you have 2 loops that you can connect up. But in reality, we're going to do something a little bit more like this, which we call a coax. Because we have a conductor in the middle on the outside, but it's exactly the same. Also, I didn't note, but the nice thing about a solenoid is that you have a relatively cheaper magnet. Solenoids are easier to come by than toroids, still expensive. Okay, so again, progress on meter cubed. All of these things are preliminary. Okay, so we've been doing lots of work on simulations. On the left here, we have a simulation that was run by an engineer at SLAC, Wes Craddock. You can see right here, this bottom part is the top, the top part right here. So we're just looking at this region. So we need a very high magnetic field inside the solenoid for the axons to interact with. But we're also using superconducting quantum sensors, which really don't like high magnetic fields. And so Wes has come up with a bucking coil and shielding scheme in order to get really low fields right in the central region, which is where we're going to put our superconducting sensors. This on the right is another simulation of that coax. You can see here is the magnetic coils right here. There's the bucking coil. Again, high magnetic field right here where we're sensitive, and then up here is where we put our sensors. We've been using simulations like this to make sure we reach the sensitivity that we want as this sort of lump element approximation breaks down. Basically, we're getting closer and closer where the wavelength is very close to the size of this experiment. And so one thing we've discovered that we need to do is that we can't actually just use one coax to cover the entire frequency range, because at that sort of 200 megahertz number that we're trying to reach up to, the wavelength is just too small. And so what we're going to do is we're going to have a series of coaxes, some for the lower frequency part, which are this height, and some which are a little shorter for the higher frequency end. And so what we've discovered is that with 6 coaxes, we can reach the entire sensitivity that we want down to the bottom of the FSE. And so there's a paper where we go through this in some detail about how this is actually going to work. But it works. Yeah.
Question. So your sensitivity that you showed, that's b to the 4 power times volume cubed.
Yeah.
So my question, one of the questions was that for a given volume, so first of all, D field is obviously that's time frame.
Yes.
And you try to do within available superconducting magnetic nodes, right?
Mm-hmm.
So that's the limit. It is a certain.
Yeah, I would say that maybe money is more than available technology, but yes.
And then the volume, try to get as big as possible. And for a given volume, can you remind me the aspect ratio of the height versus width? Is that what you're trying to say, that you take many different coaxes with different aspect ratios?
Not exactly. So the aspect ratio does matter in terms of maximizing your sensitivity, but basically what happens is that if you have, like, you can think about like a standing wave inside here, then you will sometimes have a cancellation of your voltage. So basically what you're trying to do is you're trying to say, I want to make sure that I'm not near that lowest TM0 mode. I don't have a standing wave that exactly fits inside here. And so you literally can just like shorten this, and that's how you're avoiding it. You don't have to. So yes, ultimately we will do some optimization of this, partially because we want to have the best overlap with the magnetic field and the coaxial structure. But really, we just need to shorten it. We just need to get farther away from that wavelength.
Thanks.
Yeah. Okay, yes. So we have a 6 coax sort of strategy in order to do this. This is sort of a proof of concept. Once we have a completed magnet design, we will go back through this and re-optimize, of course. Another thing that I've been working on some is the amplifier chain. In order to maximize our sensitivity, we needed to figure out what the sort of best strategy was to couple our squids to our system. And it turns out that the best way to do this is using really old sort of 80s technology squids with a very weak input coupling, coupled with a much more modern amplifier at the end. And so we're putting out a paper soon describing this, but it's sort of an unusual and very fun device. On the left is just an example squid array of something that might be used for the sort of second stage of squids. We also have to think about tuning elements. So because we're so close to these resonances, we really have to be very aware of any parasitics that are entering our system. Because again, if you add any little inductance or capacitance, you could bring those resonance frequencies down into your range. And so instead of just having a tunable parallel plate capacitor or something similar, like we're doing for the other experiments, we're actually starting to think about how we can do with coaxial tuning. So this is just a conceptual design of a tunable inductor, where basically you take this central element and you push it down in here, and that changes the effective inductance of this coax. We now have a rotation student who's doing tests on real devices. So far, she's just been testing sort of things we have around our lab, but she's shown that this method works. And then she's going to build a coax and start testing that to see if we can get the sort of tuning range that we want out of these coaxial structures. So that's where we're at right now with meter cubed. It's a lot of sort of early stage design stuff. But ultimately, we want to build this larger experiment, which is DM radio gut. So DM radio gut is going to be a definitive QCD axion search down to this most well-motivated axion space. This is the nano-EV axions that correspond to that gut scale physics. This experiment is not something we could build today. We're not quite ready there technologically. But we've laid out in this paper, what are the different R&D paths we can take in order to get there. So in that paper, we wrote down several different scenarios. Basically, we need to have some combination of a strong and large magnetic field, good coupling, good quality factors, and low noise. And so with a baseline design that we think is feasible, we would have a total scan time of around 6 years. But depending on how the R&D goes in these different areas, it could be anywhere from 3 years to 11 years to achieve that full sensitivity across that mass range. So these are the different R&D paths that we need to develop. So first of all, we need to improve magnet technologies. Right now, large magnets are very hard to build and very expensive. There's already been a lot of work on magnesium tin magnets. They already use those for accelerators. And there's also been recently a lot more work on high temperature superconducting magnets, especially in the fusion community. And so we're hoping to piggyback on that work to build this large magnet. Just for reference, this is sort of current and near future magnets. This is the radius of the magnet versus the strength of the magnetic field. Baseline design of gut is somewhere up here. So this really is like a future large scale experiment, but it's not so far away. We do think this is possible. The next thing is developing quantum limit evading amplifiers. So at these low frequencies, we're actually really buried under thermal noise. So you would initially think that it doesn't really help to get rid of quantum noise, but it turns out that you can actually increase the bandwidth of your search, so you can scan faster. And that's what we really get out of doing this quantum evasion technique. And so this is work that's also going on at Stanford. It's not quite ready yet, but we are going to be developing it for DM radio gut and testing it on DM radio 50 here. And then finally, we want to improve our resonators. So I said we already have resonators that have quality factors around 10 to 5. For gut, we'd like somewhere in the range of 10 to the 6, 10 to the 7. You can either do this in a passive way, where you just do a really good job with your materials and your surfaces, or we have some folks who are thinking about ways to do this with active elements. So Chelsea Bartram at SLAC, in particular, is the one who's doing this. Basically, you put active elements in, and you can sort of artificially improve your quality factor. Okay, so with that, I just want to summarize. So axions are a highly motivated dark matter candidate. And with the abracadabra 10 centimeter experiment, we proved that we can use a lumped element approach in order to detect them. And now we have this suite of larger experiments that we're preparing for, which is DM radio, and they will be able to probe this most well-motivated parameter space over a wide range of masses. And so I will just thank my collaborators on abracadabra and DM radio, and I will leave you with the vision for the future.
Question for
yeah.
Question, what's your squid? Can you go to the squid?
The 1 per meter cubed?
Yeah. What's your squid bandwidth that you use?
So we're hoping to go up to 200 megahertz.
200.
Yeah.
And what's the current technology?
So we don't have a physical one yet, but this is using like the old like Kesha and Clark squids for our first stage.
Those are like megahertz.
No, they actually showed up to 300 megahertz.
They do?
Yeah. They're not super linear up to 300 megahertz, but we don't need to go quite that high. So
300.
yeah. Yeah, the thing that's really great is, so basically these old style squids, everything, all the new style squids for most applications, you really want to have a very strong input coupling. That's how you get so much advantage. But when you have a resonator coupled on your input, it turns out that actually doesn't help you. We don't need to have a strong input coupling. So we can go back into that low input coupled regime where things are really nice, things match the theory, and you don't have to worry about weird nonlinearities that mess things up as you go to higher frequencies. Yeah.
So the question. Yes,
Yeah.
Plans for the frequency gravitational wave reflection, sort of the other setup for that.
Yeah, so abracadabra 10 centimeter has in it right now, I don't know if the data is like physics quality data yet, or if it's still just commissioning data. Basically, if you put a figure-8 pickup loop instead of a circular pickup loop, you have a very nice collector for gravitational wave searches. So right now, average 10 centimeter is basically just a demonstrator to show that we can run an axion search and a gravitational wave search at the same time. And I see no reason not to implement that in the 50-liter and gut experiment once we have it ready. We're not implementing it right now because Abra is still demonstrating it. I don't know if the meter cube geometry works because it's solenoid. I haven't thought about that yet. But yeah, especially for gut, for such an expensive experiment, we want to have all the physics cases. So definitely gravitational waves would be one of them.
Other questions?
Remind me, like, what happens to a stream? What comes through? Like, what's the signal on your detector look like?
Yeah, I wonder, I might have a backup slide. Let me check. Yes, I do. So basically this standard halo model shape, just like the baseline, is determined by the velocity distribution, right? So you have this like tail where you have axions that are moving with very high relative velocity to us. If you have a stream, you expect the axions to have a much tighter velocity distribution. You expect them to be going similar velocities to each other. And so you'd have a much narrower distribution and it would be some velocity on this tail. So you'd expect this baseline standard halo model, and then you have a peak at the velocity of that stream.
Okay, so in terms of like what you see in your detector, like how does that manifest itself?
So basically this template that we're looking for, we would have a template where we have this additional parameter, which we have, which is, or two parameters, I guess, whatever, the frequency of the stream and however any accidents there are in the stream, but what percentage of the halo locally is made up of stream axions versus,
Okay.
yeah.
Is it fair to say that the stream is not going to speed up the axion search? The signature is still the same.
Yeah, it's not like distinguishes from like a, yeah, okay, so maybe I'm thinking like, yeah.
So it actually can be depending on the properties of the stream. So if you think about it as if all of your dark matter was in the stream, you would have a very tall peak at a very specific frequency, and that would be a very distinct signature.
Okay, that's what I guess
right?
I'm looking for, right? You'd be sort of like focused on.
Yeah, and then depending on like the modulation signal, maybe it has a certain direction and you can see things moving around. But like, it depends on the properties of the stream, how much of that.
But that was like probably an extreme case.
Right,
But you
right.
still have to scan the frequency.
Yeah,
So
so
it
yeah.
doesn't speed up the project.
No, it does not speed
The
that.
signature gets stronger, but the speed of search doesn't.
Exactly.
Okay. Yeah, right. Yeah, your sensitivity does not become perfect.
If we knew that we were looking for it, we could scan faster, right? But we don't know. So yeah, there's a really nice paper with, I think it's Ben Sofke and Yoni Khan talking about this. If you're interested in learning more.
Okay. So other questions? I actually have one question.
Mhm.
So when you show the sensitivity regions of the dark matter radio.
Yeah.
So somehow, so the future the experiments would not be sensitive to beyond the diffusivity axion models.
Mhm.
But, this seems like a dark DM radio 50 meter. So it's just sort of the flattish, like a horizontal line.
Mhm.
DM radio and the DM radio meter cube.
Yeah.
Why?
So-
16.
Yeah, so this shape is actually determined by our scan strategy. So basically, we're scanning each individual frequency for a certain amount of time, and if we want to reach lower in gamma, we scan there for longer. And so here we're just basically scanning for the same time at each frequency, and here, because we want to reach the bottom of this QCD band, because of the sort of theory motivation, we are changing our scan strategy in order to do that.
So
Now-
you're not interested in axion like a particle.
So I would personally love to scan below this line. I think there's actually a lot of really good reasons to at least scan a little bit below this line. Something that all axion experiments do, which I don't have control over, is that we use 0.45 GeV per centimeters cubed as the local dark matter density, which is pretty outdated. But all of the experiments do it, so we can't not do it, or else our limits would look really bad. And so like if that is correct, that it's 0.3 GeV per centimeters cubed, we actually are sitting up a little higher in this band, so that's kind of unfortunate. And then also there's some theory uncertainties in this band. So my understanding is that it can't change a lot, but you could go down on some amount. But all experiments do this because it takes a really long time to get higher sensitivity. Basically, the scaling goes as time to the 1/4. So if you design your experiment to reach here, to reach just a little bit farther down takes a lot more time, and so that gets really expensive. So this is how we design our experiments. Maybe it's 0.6 GeV per centimeters cubed, and then we'll get lucky. Yeah.
Okay, so yeah, that makes sense. Okay, so other questions? If not, let's take the speaker. Okay, so then she's gonna be here, with us